Alright everybody, so we're going to take a look at Lewis structures and how we go from that 2D Lewis structure to a 3D VSEPR, and then we'll be discussing polarity as well. For these problems, you should have already drawn the Lewis structure. This is from worksheet 3, so you can look there and just copy that, or you can just practice and draw the Lewis structure again. We will look at electron domains and we'll write the electron geometry, and then we'll look at the bonding domains and lone pairs and we'll write the molecular geometry. We will draw what that looks like in 3D space, and then we'll take a look at electronegativity differences and indicate any bond dipoles, and then determine if the molecule is polar or nonpolar. So let's take a look at number 1 in H3. So I already have the Lewis structure drawn. So if we're looking at electron domains, then we are going to see that we have 4 electron domains, 3 bonding and 1 lone pair. Our electron geometry in this case is going to be tetrahedral because of those 4 electron domains. For molecular geometry, we have 3 bonding, but that lone pair still impacts the shape, and so this is going to be called trigonal pyramidal. If we draw this with our VSEPR kind of 3D representation, we would have 1 hydrogen that would be in the plane of the paper, and then I'm going to draw those lone pairs of electrons. I know that that's, they're not actually going to have a little bond, but they would be still in a certain plane, so they could be in the plane of the paper. We would have a hydrogen coming towards us and a hydrogen going into the paper. Okay. Now for our bond dipoles, we need to take a look at electronegativity differences, and so you'll have access to this. This is looking at electronegativity, so we have nitrogen, which is here. The electronegativity is in this circle here, so that's 3. And then hydrogen is 2.1. So for our electronegativity, we have 3 minus 2.1, so that's a 0.9 difference. So that means that we're going to have polar bonds. Our dipoles then that we would draw is we would draw them going this way towards nitrogen. And we would have a partial positive on all the hydrogens and a partial negative on the nitrogen. Now, the next question is the molecule polar or nonpolar? And so this would be a polar molecule because it is asymmetrical and all of the bonds are polar. Okay, so let's take a look at SiH4. So I've drawn the Lewis structure. We have 4 electrons and 4 bonding domains as well, so this means that the electron and molecular geometries are the same. So we have tetrahedral for the electron and tetrahedral for the molecular. We have Si, silicon in the middle. We have 2 hydrogens that are going to be in the plane of the paper, 1 that's going to be coming out towards us, and 1 that's going back into the plane of into the paper. Okay. All right, if we look at polarity and bond dipoles, we will take a look at the electronegativity values. So we have silicon is 1.8, hydrogen is 2.1. So we would have 2.1 minus 1.8, so we have 0.3 difference. So this is going to be nonpolar bonds. So this would be Na or nonpolar bonds for this. So there would be no bond dipoles drawn, and it would be a nonpolar molecule. Okay. All right, so for our last one, we'll take a look at selenium fluoride. So I have drawn what we need to have drawn. So we have 4 electron domains and we have 2 bonding domains. We're going around the central atom selenium, so we're going to have tetrahedral for our electron geometry, and then we're going to have bent for our molecular geometry. So whenever I draw this, what I normally do, I draw selenium in the middle. I draw 2, so you could draw a fluorine here and a fluorine here, and then you could draw your electrons coming out and in. Selenium wanted to disappear. Okay, or you could draw it like this, selenium you have 2 that are in the plane, and then you have electrons that are coming out and coming in. So you can draw it either way. Oops, and they're not hydrogens, they're fluorines, but you get the picture. Okay, let's take a look at polar bonds. So if we look at selenium, 2.4, and then fluorine, 4.0. So we're going to have 4.0 minus 2.4, 1.6. So that's a pretty polar, pretty strongly polar bond. It's going to go from selenium out to fluorine. So that would be our bond dipole there. We would have a partial negative on the fluorines and a partial positive on the selenium. So whenever we look at, is this a polar molecule? It is a polar molecule. It has those lone pairs and that bent configuration for the molecular geometry, and so we would call that a polar molecule.